So in this lesson, we're going to look at how the continuous distribution function can be useful for calculating the median, quartiles, and we'll have a look at the mode. So in a continuous random variable, I've said before that the height of the function is not the probability itself, but it is the likelihood. Wherever we find a peak or the greatest height within a valid range is going to be the mode. The median, we can use a cumulative distribution function, and if we set it equal to 0.5 and solve for the unknown x value or solve for the m, we're going to be finding the x value that has 50% below it, the x value that has an area of 0.5 below it, and this by definition is the median, the value that has half of the distribution below it and half of the distribution above it. Similarly, we can find the lower quartile by setting the cumulative distribution function equal to 0.25 and the upper quartile by setting it equal to 0.75. Percentiles, set it equal to the appropriate value. The definition of the mode that you've learnt up to now is going to be the value with the highest frequency. Well, that's equivalent to saying the value that is most likely to occur. In a continuous random variable, I've said that the height of the function is not the probability, but it is the likelihood, and we're just looking for the value with the highest likelihood. We're looking for the highest point of the function in between the valid interval. So, depending on the shape of the function, we can find this either by inspection, or through differentiation, or a combination of the two. Okay, so let's look at a range of examples here. We're going to try and find the mode for each of these, but we need to really consider the function that we're working with. And a visual to consider is actually going to help us make sure we get the correct answer. So, this first function, what type of function do we have? Looking at the maximum power of x, we're going to get x to the power of 3, a function of order 3. This is a cubic. For me to be able to sketch this cubic, I want to be able to think of all of the roots. So, set the function equal to 0, I have a repeated root at x equals 0, and I have x equals 1. And this is a decreasing function. So I expect my sketch to go like this. Now this function is only valid over the interval 0 to 1. So actually, I'm going to try and make a solid line off the interval that we're actually interested in. So right here from 0 to 1. The mode is going to be the highest point of this section. So actually, I realize I can differentiate and find the mode in this particular question. So let's go ahead and do that. So differentiating the function, so I'm just going to expand the function out in the first place, and differentiating gets us 24x minus 36x squared. Factorizing that gives us 12x and 2 minus 3x as factors. That either gives us x equals 0 or it gives us x equals 2 over 3. Looking back at the graph again, x equals 0 would not make sense for the mode. Yes, it's a turning point, and that's the reason we differentiated to find the turning points, but only one of them makes sense in this particular case. Without the sketch, you wouldn't necessarily know which of these turning points would represent the mode. You can't discount 0 just because it's a 0. We could have 0 being a mode. You could end up differentiating for a second time to find the nature of the turning point, but as you'll see in a few moments, even that isn't enough to know for sure that that turning point is the mode. We really need a visual representation of the function to make sure we get the correct value for the mode. In this case, the mode is x equals 2 over 3. Okay, for the second one, for the g function here, what kind of function are we working with? Well, this is a linear function, and it's a linear function with a positive gradient. It's an increasing function. This would be my sketch. From here I can see, just by inspection, that actually the mode is just going to be the highest point. With an increasing function, that means it's just going to be the largest of the two limits. If this was a decreasing function, similarly by inspection, we would know that the highest point of the function within the valid interval would be the lower limit of the interval. So for linear functions, it should be quite straightforward. Differentiating here would get you nowhere. I've seen lots of students who just think in their head, to find a mode, I'm going to differentiate. And without the visual, without considering the type of function you're working with, that won't always get you to the correct solution. Okay, and the third function here, so this h function, we once again have a quadratic. So I want to consider what this function would look like. So let's set it equal to 0, so we can try and factorize. If we factorize, we can find its roots. So factorizing leads to roots where x equals 4 and x equals -2. So let's just get that on a diagram. -2 and 4 are the roots. We know by symmetry this maximum point must occur at 1. And checking the valid interval, this function is valid in between 0 and 4. So this highlighted section is what we're actually interested in. Looking at this, I can verify that the turning point here is going to be the mode. Okay, by inspection, and because I know about symmetry with quadratics, I know that the mode is going to equal 1, but some students will insist on differentiating or may not have noticed that we have the symmetry to rely on here. So let's just check what happens if we differentiate. So differentiating once again leads to that same result, x equals 1. Okay, just before we wrap up, I do want to show you a couple more cases to exemplify why we can't just rely on differentiation, and we should really get a good idea of what the function looks like. Here we have the same function twice, and depending whether the interval we're interested in is 1 to 3, or if the interval we're interested in is 4 to 6, we can see that in both cases, the mode has nothing to do with the turning point. The turning point here wouldn't actually give you the largest value of the function. It wouldn't give you a peak. This is a minimum point. So differentiating will be absolutely useless here. We need to consider whether or not the function is increasing or decreasing over the interval we're interested in. In the first example, it would be the lower limit, the value of 1, that leads to the mode. In the second example, it will be the upper limit, the value of 6, that leads to the mode. Without a visual representation, we're really just trying and testing our luck to see whether or not we calculate the mode correctly. So let's actually have a look at how we can use the cumulative distribution function to calculate the median and also the quartiles. So firstly, we were given the PDF and we need to find the cumulative distribution function for ourselves. As usual, I'm going to factorize out any constants and I'm going to integrate. So 4 comes out and I'm integrating x minus x cubed. That gives me a half of x squared minus a quarter x to the power of 4, limits x and 0. Substituting in and expanding, I'll do it all in one go. We get 2x squared minus x to the power of 4. The complete cumulative distribution function has that function in the middle, and I've also got my 0 and my 1. To calculate the median, I'm going to set this function equal to 0.5. And that leads to I'll swap the x for an m, 2m squared minus m to the power of 4 equals 0.5. I can rearrange this, and at this point I'll notice that this is a hidden quadratic. I can let y equal m squared, and I have the quadratic y squared minus 2y plus 0.5 equals 0. Solving this, I get y values of 0.2926 and 1.7071. Square rooting each of these gets me 0.5409 and 1.33066. Checking the original limits, 1.3 is beyond the valid range, so I know that the median value must be 0.5409. We can check this, we can test this value by substituting it into the cumulative function, and we get very close to 0.5. It's only a rounding error that moves us off of 0.5. So this is how we process the median. We set the cumulative function equal to 0.5, solving for x lets us know the x value that would lead to a probability of 0.5 below that x value. Let's have a look at where we have multiple functions and we're actually looking for the interquartile range. The first step that we need to do here is to actually check whether or not the quartiles or the median or anything that we're looking for is going to exist in the first interval or in the second interval. So we're actually going to maximize the first interval, and I do that by substituting the largest value of the first interval, which is 2, into the function. So capital F of 2 gives us an answer of 1/5 or 0.2. So I'm just going to actually just consider, does this interval, is it going to contain a median? It's not, because we've only got up to 0.2. Is it going to contain the upper quartile? Well, if it doesn't have the median, it doesn't have the upper quartile. Is it going to contain the lower quartile? The lower quartile would be a probability of 0.25. So actually, this first interval doesn't have any of the quartiles that I'm looking for. It would have the 10th percentile, it will have the 15th decile, but it doesn't contain any of the quartiles. This is still a very important step for you to do. We do need to check whether or not any of the values we're looking for exist within that first interval. Since they don't, we'll just move on to the second interval, and we'll use that to calculate the lower quartile and the upper quartile. For the lower quartile, we know that this function should be set equal to 0.25. We can do that and rearranging to find a quadratic that we can easily solve with our calculator's quadratic equation solver or any other technique you want to use. This leads to two values, x equals negative 0.224 or x equals 2.2247. Every time I get a set of values, I'm going to go back to the interval and consider which of those is going to make sense for the interval this function is valid for. This function is valid in between 2 and 4, so it must be the 2.2247. Okay, a similar thing for Q3. This time we'll set the function equal to 0.75. We'll do our rearranging again, and we have another similar quadratic to solve. This leads to two answers, negative 1.549 and 3.5495. Which of these are going to be sensible for the interval the function is valid for? It's the 3.5495. And the interquartile range, as always, is Q3 minus Q1. What's the difference in between the two quartiles we've calculated? In this case, 1.3248. Okay, so making use of these techniques, we should be able to find a range of statistics that will be useful to us. So in this section, we're going to have a look at skewness. Skewness refers to the shape of the distribution. We've seen a few different shapes before. We have seen a uniform distribution where the frequencies or the likelihoods are all the same. We've seen a symmetrical distribution. We saw this both numerically, visually on a diagram. More specifically today, we're going to look at both positive and negative skew. How can we find these without the visuals, without the diagrams in front of us? So, for a symmetrical distribution, we actually expect these three statistics, the mean, the median, and the mode, to be approximately equal to each other, to all line up right in the middle. This is a feature we would expect from a symmetrical distribution. Additionally, if we saw a box plot or we were working with the quartiles, we would expect the gap between Q2, the median, and the lower quartile to be approximately equal to the gap between Q3, the upper quartile, and the median. So we can use either of these comparisons as a way to describe or determine the skewness. This is what we would expect for a symmetrical distribution. For positive skew, in positive skew, the high values are skewing the mean for it to be large. The most likely value from the distribution we know to be the mode, and the median typically stays in the median. So looking at positive skew, the mode would be the lowest of the values, followed by the median, followed by the mean. On a box plot, this is what we would have, and a comparison of the quartiles says if Q2 minus Q1 is smaller than Q3 minus Q2, that's an indication of positive skew. Negative skew is the inverse. The mean is being skewed really low by the smaller values. The mode, once again, is the most likely. It's going to be the highest point of the sketch. And the median, once again, is typically located in the middle. If the mean is smaller than the median is smaller than the mode, we have negative skew. And we can make a comparison with the quartiles, just like I'm showing here. When we're comparing these statistics, the mean, the median, the mode, we don't have to have all three. Any pair of them we can use to make the comparison. So for negative skew, if I only have the mean and the mode, if the mean is smaller than the mode, that's enough to justify my definition. If I only have the median and the mode, if the median is the smaller of the two, that's enough to justify my comparison. Usually when you're asked to determine the skewness, you would either have found some of these statistics or you would have found the quartiles. You don't necessarily need to go and calculate anything additional, just use what you've already calculated so far in the question.